Pluto, once considered part of our planetary system, remains a distant and perplexing celestial body. Recent statements from prominent astrophysicists like Neil deGrasse Tyson and Michio Kaku have thrust Pluto back into the scientific spotlight, suggesting a surprising new theory. This frigid world could potentially collide with Neptune. This raises several critical questions. How could such a collision occur, and what would be the consequences of such a monumental event? Is this just an intriguing yet improbable theory, or is there a deeper, more significant impact in store? Join us as we explore the possible effects of a Pluto-Neptune collision. Pluto, formerly classified as a planet but later reclassified as a dwarf planet, continues to intrigue the scientific community. Its peculiar orbit makes it an ongoing subject of study. According to recent findings from leading experts, Pluto's orbit comes alarmingly close to that of Neptune, prompting concerns about a potential disaster. But how likely is it that such a collision could happen? Pluto's journey around the Sun is distinct from the other planets. It takes a long 248 years to complete a single orbit. This means that since its discovery in 1930, Pluto hasn't yet finished one full orbit. But Pluto's eccentric orbit doesn't end there. Its path is markedly different from the almost circular orbits of the major planets, and it is tilted at an angle of 17 degrees relative to the plane of the solar system. Pluto's path follows a significantly steeper trajectory than the other planets. A particularly fascinating aspect of Pluto's orbit is its periodic intersection with Neptune's orbit. For about 20 years during each orbit, Pluto comes closer to the Sun than Neptune, which is a surprising phenomenon given their positions in the solar system. This naturally leads to the question, why hasn't Pluto collided with Neptune? The answer lies in the gravitational influence of other planets. When Pluto's orbit was first analyzed, astronomers were perplexed by its unusual characteristics. Unlike the orbits of other planets that mostly lie close to the ecliptic plane, Pluto's orbit was notably tilted and curved. This raised additional questions when astronomers realized that Pluto's orbit crosses that of Neptune. The study of this phenomenon highlights the complexity of space dynamics, especially when it involves multiple celestial bodies influencing each other's movement. The three-body problem in space describes the challenge of determining how three celestial bodies, like Pluto, Neptune, and the Sun, interact through their gravitational forces. Pluto's orbit is particularly chaotic. Even the smallest changes in the initial conditions could lead to drastic shifts over time. However, these same irregularities have been found to stabilize over long periods. Simulations have provided more clarity on how planets like Neptune, Jupiter, and Saturn keep Pluto's orbit in check, ensuring stability over billions of years. Without the gravitational forces of these larger planets, our solar system would be far more chaotic. Pluto's orbit offers a textbook example of both stability and disorder in celestial mechanics. While the path is irregular, it has remained surprisingly stable over time thanks to the forces at play from neighboring planets, especially Neptune. Predicting future celestial events, particularly with unstable orbits like Pluto's, is incredibly difficult. The inherent unpredictability of such systems makes long-term forecasts uncertain. While computer simulations have advanced our ability to model the behavior of planets and other celestial bodies, they also reveal the limits of our predictive power. This leads us to the question, why are respected astrophysicists like Neil deGrasse Tyson and Michio Kaku only now warning us about a potential Pluto-Neptune collision? Despite the various stabilizing forces, they have expressed serious concerns about the possibility of Pluto colliding with Neptune. Such an event would undoubtedly be catastrophic. The collision would release an enormous amount of energy, most likely destroying Pluto due to its smaller size and icy composition. The debris from the impact could scatter across the solar system, possibly posing a risk to other planets and their moons. For Neptune, the collision could alter its atmosphere and even affect its orbit, depending on the severity of the crash. Michio Kaku, an expert in theoretical physics, brings a unique perspective to this discussion. His work in string theory and his broader views on space exploration help us understand the deeper connections between celestial mechanics and theoretical physics. Understanding the gravitational interactions and orbital dynamics of bodies like Pluto is crucial for planning future space missions. Such knowledge not only aids in exploring the outer planets, but also helps predict and mitigate potential dangers in the solar system. The implications of a Pluto-Neptune collision go beyond just the destruction of two celestial bodies. The event could provide valuable insights into the physics of extreme energy and gravity. The collision might create conditions where predictions from string theory become observable. String theory, which posits that fundamental particles are one-dimensional strings rather than point-like objects, could potentially offer explanations for such high-energy phenomena. This collision might shed light on how fundamental forces and particles behave under extreme conditions. While the actual impact on Earth would be minimal due to our distance from the outer reaches of the solar system, the scientific consequences could be groundbreaking. The event would offer a rare observational opportunity to test key concepts of string theory and other areas of physics. Pluto's unusual orbit, with its distinct characteristics, continues to fascinate scientists, providing a glimpse into the intricacies of celestial dynamics. The reclassification of Pluto as a dwarf planet sparked considerable debate, but recent revelations about its orbit have reignited interest in its role in the solar system. Tyson and Kaku have both raised alarms about the potential risks posed by a collision between Pluto and Neptune, emphasizing the delicate balance of forces at play. Pluto's path, with its steep inclination and eccentric orbit, defies conventional understanding of planetary motion. Unlike the near-circular orbits of its planetary neighbors, Pluto's orbit crosses Neptune's, complicating predictions about future interactions. The role of gravitational forces from other planets, particularly Neptune, is crucial in maintaining Pluto's orbit. Despite its chaotic nature, the stability of Pluto's orbit has been preserved over long timescales due to the gravitational influences of Neptune and other larger planets. Mathematical models and simulations play a critical role in forecasting the movement of celestial bodies, and they help us understand the complex gravitational interactions between planets. Although Pluto's orbit is unstable over centuries, it remains relatively steady in the larger context of the solar system's gravitational framework. The possibility of a collision between Pluto and Neptune, while speculative and unlikely in the near future, highlights the unpredictability of celestial dynamics. The warning from experts like Tyson and Kaku serves as a reminder of the constant flux in our solar system. While such a collision remains improbable, it underscores the complex balance of forces governing the movement of celestial bodies. Beyond its scientific relevance, the study of Pluto holds practical importance for future space exploration. NASA's New Horizons mission, which launched in 2006, provided unprecedented images and data of Pluto and its moons during its historic flyby in 2015. New Horizons revealed previously unseen details about Pluto's surface, such as vast fields of frozen nitrogen and sprawling plains of water ice. These findings expanded our knowledge of the geological processes shaping distant planets and further demonstrated the technological advancements required for deep space exploration. The success of the New Horizons mission also emphasized the importance of international collaboration in studying distant celestial bodies. By examining Pluto, scientists have gained insights into the conditions of the outer solar system, which could inform future missions to other distant objects. The ongoing debate over Pluto's status as a dwarf planet is reflective of larger questions about how celestial bodies are classified. While Pluto meets several criteria for being a planet, its reclassification sparks discussions about how science evolves and the way in which we categorize astronomical objects. Studying Pluto's orbit and interactions with other planets deepens our understanding of planetary motion, celestial mechanics, and the formation of the solar system. By learning from Pluto's unique orbit, we can better understand the dynamics of other distant worlds. The discovery of Pluto also provided key insights into the Kuiper Belt, a region beyond Neptune that is populated by small icy objects. Studying Pluto's orbit offers clues about the gravitational forces that may have influenced the early formation of planets. This understanding is vital for developing theories on the solar system's origins and the processes that shape planets over time. Moreover, understanding these celestial mechanics could play a critical role in future space exploration efforts, particularly in identifying potential targets for future missions. While the likelihood of a Pluto-Neptune collision remains low, it serves as a reminder of the unpredictable nature of the cosmos. As we continue to explore the outer regions of our solar system and beyond, the study of planetary orbits and celestial dynamics will remain a core area of research. Pluto's distinctive orbit offers a wealth of information about the forces at work in our solar system, and the ongoing investigation of its behavior provides valuable insights into the broader workings of the universe. With every discovery, we refine our understanding of the cosmos, uncovering the mysteries of distant worlds and deepening our grasp of the universe's fundamental principles. Pluto's orbit is an exceptional case in the study of celestial mechanics, and the idea of a potential collision with Neptune serves as a thought experiment that stretches the boundaries of what we know about gravitational forces. Although the concept of Pluto's orbit being unstable may seem alarming, it provides an opportunity to reflect on how planetary bodies interact and the long-term stability of the solar system. The unique characteristics of Pluto's orbit also underscore the delicate balance of forces required to maintain harmony among the planets. A collision, though improbable, offers a window into how dynamic interactions can influence planetary systems. Astrophysicists often use models of orbital dynamics to understand how gravitational interactions between planets, moons, and other celestial bodies affect their movement. Pluto's orbital path, tilted and eccentric, gives scientists valuable insight into these models, which are critical not only in predicting planetary movement but also in understanding how smaller bodies, like asteroids or comets, might interact with larger planetary systems. While the likelihood of a Pluto-Neptune collision remains remote, it reminds us of the complexities that govern the motion of all celestial bodies, from the smallest dwarf planets to the largest gas giants. In addition to these theoretical considerations, there are practical implications for the study of Pluto and its potential interactions with Neptune. As space exploration continues to advance, understanding the orbits and positions of objects in the outer reaches of our solar system will be critical for planning future missions. The possibility of such a collision could provide an opportunity for space agencies to deploy advanced technology to monitor these bodies and analyze the changes in their orbits. Additionally, studying how gravitational forces might change the trajectory of Pluto's orbit could lead to advancements in our ability to detect and track other bodies in the Kuiper Belt, a region beyond Neptune that remains largely unexplored. There is also the broader question of how celestial objects form and evolve over time. While much attention has been given to the inner planets and their formation, the outer regions of the solar system are equally important in understanding the early stages of planetary development. By studying Pluto and similar objects, scientists can learn about the conditions that existed in the early solar system and how these distant bodies contributed to its formation. This knowledge may provide clues about the processes that led to the creation of the planets and the overall structure of the solar system as we know it today. Moreover, the potential for a collision between Pluto and Neptune could shed light on broader cosmic phenomena, such as the behavior of celestial objects under extreme conditions. For example, this event could lead to the release of gases and materials that are not commonly found in other parts of the solar system. Such findings would not only expand our knowledge of Pluto and Neptune, but could also deepen our understanding of how the forces of gravity and energy influence celestial bodies in other parts of the galaxy. These insights might one day play a role in the exploration of exoplanets and the search for life beyond our own solar system. The future of Pluto and Neptune will remain uncertain, but what is certain is that their continued study will provide valuable information about the universe and the laws that govern it.